Continue today with the wind loads lecture, finish that up. There's an example that I'll just kind of talk through as a way to recap the process and show you how it can be applied to a building. And then I have a few other things to share as well. So before we get started, do you have any questions? Homework 6 went well, I imagine. Haven't taken a look yet, but saw that it was most submitted by most students, so that's a good sign. Homework 7, as I mentioned, is due next Wednesday, so a week from today. It will cover dead loads, live loads, seismic loads, and wind loads. So, welcome. All right, so I think this is where we left off, right? We were talking about exposure category. So I talked about how exposure B is related to kind of suburban or now also urban areas if you're not doing a wind tunnel test for an urban area. And exposure B would be the best case scenario for wind loads because all those obstructions provide the most protection against the wind. However, there are circumstances where surrounding buildings or obstructions can create undesired effects on your building. And that's a situation where you would want to use a wind tunnel test. So there could be things like channeling, buffeting. Those are all terms that you don't need to know for this class. But those are all effects that can happen if there are, certain types of surroundings in your building. And we'll look later at some examples of wind tunnel test setups so you can see kind of how involved those can be. Exposure C would be more wide open spaces. And I mentioned, I think where I left off was the fact that in Bozeman, the city of Bozeman building code says use exposure C for all buildings in Bozeman. There really isn't a scenario in Bozeman where exposure D would apply, because exposure D is for flat open surfaces like open water or mud flats or ice. So all the open flat fields that you see around here would fall into exposure C category. And then I mentioned that even though there are some areas within Bozeman that could technically be, it's arguable that those could technically fall into the exposure B category. Because the code says exposure C, that means the minimum requirement is to use exposure C. That being said, as the structural engineer of record or the design engineer, sometimes you can make a case, you can argue your case if you believe that it should be something different from the code that's less conservative but more accurate. Sometimes you can argue your case and then the authority having jurisdiction would just have to approve that. So you just have to submit your case for approval. Something like exposure category probably isn't worth your time and effort to argue over. So it would just be easy to use exposure C. All right, so that brings us to the next coefficient to define, which is the topographic factor, KZT. Now in this class, we're only going to be worrying about cases that have flat topography. And in that case, it's very simple. You just use a factor of 1 for this KZT. But if you had a scenario where you had to calculate or consider a value that's not 1 for KZT, then you would use this figure, all right, where it breaks down the geometry of the escarpment or ridge that is nearby your structure, all right? And based on this factor, H over LH, then where H is this distance, right? So the total height change in land around you, and then the the LH is this distance here, so it's basically half the distance, half the length. Then, based on that, you would determine your K1 multiplier. And then you'd have to calculate determine another K multiplier, K2, which is based on X over LH, where X is the upwind distance, right, to where your building is located. And then you've got Z over LH, where Z is the distance above the ground. So this K3 factor will vary with height of the building, and then the other factors will vary with other different characteristics of the topography related to your building. Let's see. Yeah, so that was kind of really more in depth than you need to know for this class, but just kind of showing you what all's involved. Once you figure out those three K factors, the K1, K2, K3, then you multiply them together, and then there's another factor. Let's see. I think it's provided on that page, which I included just for reference. Yeah. So KZT, the equation is 1 plus the product of those three multipliers, and then that quantity gets squared. But you don't need to know that stuff for this class. So this class, just understand topography is 1, but also understand that sometimes you need to calculate something else to account for that wind speed up factor. All right, so next, the elevation factor, KE. This is simple. You just enter the table with your ground elevation in feet and, or meters if you're working in metric, but in this class we're just doing feet. And then you read the elevation factor from the right column in the chart. If you are in between, you can apply linear interpolation. They also provide the exact equation to use if you want to do that. Let's see. Oh, I take that back. Don't interpolate linearly. It doesn't say that. It says, oh, it does. Yeah, it does say it. All right. Yeah, so in the second note down here, it says you can use interpolation or use the exact equation. So this factor is something that's helpful for us. As you can see, all the values in the table are less than 1, so that will have the effect of reducing our design wind pressures. And it's new in the 2016 version of ASCE 7. So before the current version, this wasn't an option, but now we can reduce our wind loads based on higher elevations. And again, that is tied to the fact that air is less dense at higher elevations, so the pressure will be less. Conservatively, you can always use an elevation factor of 1 if you don't feel like calculating it, or if you think that it's appropriate to use 1 instead. So just for context, right, we in Bozeman, we're about at roughly 5,000 feet elevation, and so that leads to a 17% reduction in wind loads, which is pretty significant. All right, so next we have the internal pressure coefficient, GCPI. And as I emphasized before, those 4 letters together represent one value. So please don't confuse that capital G with something that you have to plug in and multiply a CPI by. That's not the case. This GCPI is going to be one of 3 magnitudes, and then whatever magnitude you use, plus or minus applies, right? And really one of 2 magnitudes, because the third one is 0, so plus or minus doesn't really matter. So depending on your enclosure classification, you find your magnitude of the internal pressure coefficient, right? So most buildings fall into this first category. They are enclosed. Sometimes if you have one wall that has a lot more openings than others, you can fall into one of these categories, partially enclosed or partially open. The worst case scenario for building wind loads is the partially enclosed. So this gives you the highest internal pressure coefficient, plus or minus 0.55. And that's a scenario where the wind can easily enter a building, but it's harder for it to escape. So it can generate large internal pressures. In this class, we're only going to be dealing with enclosed buildings, really. So your coefficient will be plus or minus 0.18. You don't have to worry about how to determine the enclosure classification. So that's the rest of the stuff in this table, but we'll leave that for another class, or if it's not even, it may not even be covered in another class. That's just something that you pick up in practice if you go into structures. So this class, just worry about the enclosure classification. I'll tell you what it is. It's most likely going to be enclosed building, because that's the most common, right? All right, so this is on the, now we're nearing the end of your handout. All right, the ASC 7 handout for wind loads anyway. So this is the second to last page in the wind loads section. And this is really just useful for understanding how the pressures are going to act on the structure. So it provides some plan views and elevation views for different types of roof shapes. And in the plan views, you can see the windward, leeward, and sidewall pressures. In the elevation views, you can see the windward, leeward, and roof pressures. Now, the last page of the handout on wind loads is all focused on the external wall coefficients and the roof pressure coefficients. So this is all for calculating external pressures on your walls and roofs. We'll first look at the wall coefficients. The wall coefficient, you enter that table with the ratio of L over B. And remember, before I defined those dimensions, right? L is always the dimension of the building that is parallel to the wind direction, and B is always the dimension of the building that is perpendicular to the wind direction. So you're going to have potentially two different coefficients to apply to your building when you consider two different wind directions, right? So you have one value for your windward, well, first for the leeward wall, that is, right? So for the windward wall, it doesn't matter what your L over B ratio is. You're always going to have a pressure coefficient of positive 0.8. And note that it's the only positive pressure coefficient, right? That's because the windward wall gets that positive pressure. The other walls all experience negative pressure. So this is where that comes into play. All those coefficients are negative for the leeward and side walls. The sidewall also doesn't depend on L over B, right? So that's always going to be a negative 0.7. The leeward wall, however, is the one that can change depending on the wind direction with respect to your building. So it can be anywhere from negative 0.2 to negative 0.5. The other note that's important to keep in mind is that all of the walls, except for the windward wall, and this is also true for the roof, will use this pressure coefficient in conjunction with QH. And remember, Q is that velocity pressure coefficient. That was the long equation that where you multiply all those factors together and V squared, and then you've got a coefficient or a constant in front. So that's the Q. QH is that equation evaluated at height H, which is the mean roof height. So we use that single value with the leeward wall and the side wall. With the windward wall, we use QZ, right, which varies with height. So we will have multiple different values of QZ for different heights above the ground. Now for the roof, this is a little bit more complex. So it depends on whether the wind is going to be parallel to the ridge or perpendicular to the ridge, if your roof is sloped or flat, things like that. So the top part of this table is specific to sloped roofs where you have a slope of 10 degrees or greater. We're not going to worry about that in this class. It's just a little bit more complicated because you have to think about the angle and also that ratio of the height, the mean roof height to the length of the building, which is that dimension parallel to wind. In this class, we'll just focus on roofs that are low sloped or flat, which is in the lower portion of the table. This portion also applies for sloped roofs with the greater than or equal to 10 degree slope if the wind is parallel to the ridge, right? But in this class, we'll just deal with flat roofs. And so you enter this table with that H over L ratio, right? Now H again is that mean roof height, L is the length parallel to the direction of the wind. So based on that ratio, then you also have to think about how far you are along the roof from the windward edge, right? So from 0 to H over 2, that's the nearest section. Your CP value is going to be higher in magnitude, right, for the portions that are closer to the windward wall. H over 2 to H, same thing. If your H over L is less than or equal to 0.5, right? So then you have a negative 0.9 from 0 to H along the length, right? So basically the square. Beyond the mean roof height in length along the building in the direction of the wind, your CP value will decrease in magnitude, right? And similar for if your H over L is greater than or equal to 1, except you just have two different possible CP values, right? One from 0 to H over 2 along the length, and then it decreases beyond that. One other thing to point out in this table, let's see, all right, so I already talked about that. Yeah, and then go to that. All right, so one thing to note, there's two CP values. One of them is just negative 0.18. That's something that you don't have to worry about in this class. Technically, it's something that you should consider, and you should compare both values, the results of both values, and use the worst case scenario. But it's unlikely that that lower magnitude will govern. So it can happen in cases if you have a really high internal pressure, then it could govern your net pressure. But in this class, we're not going to worry about that. All right, so the other thing that I wanted to point out in this table is this value. If you have a scenario where your H over L is greater than or equal to 1, and in that first stretch along the length, right, oh yeah, so there's the sketch, that would have been helpful earlier. Right, so along the length, for the first half, or the first 0 to H over 2 distance, you have this negative 1.3 CP value, which is really high. But it has this footnote associated with it that says that value can be reduced linearly with area over which it applies, according to this table here. So if the area of your roof, the surface area, is greater than or equal to 1,000, then you can reduce that CP value by 20%. So, so you would take the 0.8 and multiply it by the 1.3 to get your CP value. All right, so that is the complete process for determining the design pressures. Well, we didn't combine the external and internal, but you have the equation for that, right? So those are all the steps that you need to take before you can calculate the design net pressures. This page summarizes all the steps for determining those pressures, and this is also included in your assigned reading handout, the structural loads one. All right, so that's on page 19 of that handout. And again, in this class, we only have to deal with rigid structures and flat topography, so that simplifies some of these steps, right? So for example, in this one, the topographic factor, we just fall into this first category, this first option A. You can ignore everything listed under B. But this was written out intended to be a general guideline that could be helpful for you if you go on to an internship in a structural engineering firm or a practice in structural engineering, right? Okay, any questions? Okay. All right. So we'll go through and I'm going to talk through this example, and this will hopefully help to piece together how this process works and show you how to pull all these items together, right? And also act as a summary of everything that we've talked about. So in this example, all the stuff that's in the red would be considered given information, right? So you have this building that's 100 feet by 200 feet in plan and 111 feet in height, flat roof, located in Long Island, New York. Topography is listed as flat, suburban exposure, and it's an office building, right? So what does the office building part tell us? Yeah, it's a clue as to what risk category it would be. So what risk category do you think would apply to an office building? 2, yeah. Yeah, we don't have any other information that would indicate that it stands out beyond risk category 2, right? So some office buildings could fall into risk category 3 if they have a huge number of occupants, right? So if it's a really, really large office building, much larger than this one, then it could maybe be in category 3, risk category 3 building. But most buildings will be risk category 2. Let's see, what else? All right, we're told that the fundamental natural frequency is greater than 1 hertz in both principal orthogonal directions. That just tells us that it's a rigid structure, so we can use that G gust effect factor is 0.85. We're told that it's a closed building, right? So that's the enclosure classification. That tells us what internal pressure coefficient we're going to use. And the importance listed down below, that's related to the risk category. So risk category used to be called occupancy category, I think. And so it's tied to the importance factor. But it's listed here as normal, no assembly area. All right, so that's another clue, no assembly area. So we'll use risk category 2. And since this exposure is suburban, that tells us that the exposure category would be exposure B. All right, so based on its location and the risk category, we would obtain the design wind speed from the maps, right? And we would want to use the map that is specifically for risk category 2. So remember, there are 4 maps, 1 for each risk category. So if we go to that risk category 2 map and zoom in on New York, Long Island area, right, we could see our options there range from 115 to 140. So since we weren't given exact coordinates or an exact address, we just use the 120. And then for flat topography, right, KZT is taken as 1. For a rigid structure, gust effect factor 0.85. Right, we already talked about much of this stuff. And then the wind directionality factor, KD, that's always going to be 0.85 for buildings. Elevation factor, we get that from table 26.9-1, but since Long Island is at sea level, that's just going to be a 1. We don't get to reduce it. All right, so this is where things get a little bit more involved when we have to determine the velocity pressure. So that's calculating QZ, right? So that involves all of the factors that we just identified and defined, including the main wind speed. And then also we need to determine the velocity pressure coefficient, KZ. So the velocity pressure, I think it's technically called the velocity pressure exposure coefficient. Yeah. So in table 26.10-1, That's where this list is coming from. If you go to exposure B column, right, we would select KZ from that value. So my note here too is that the heights that are listed in this table, these are specific to the building, right? So it tops out at the maximum height of the building, which is 111 feet. And then these intervals, right, beyond the 0 to 15, you can really choose as the engineer how often you want to update that value. So it's a good idea to, you know, be somewhat refined, but you don't have to go like every story necessarily. You don't have to go, you know, every 10 feet necessarily. So you can choose how often you want to increase that value. But you do want to make sure that you're not being too under conservative, right, or too overly conservative. And then the 0 to 15 is always going to be your first category. So that's always going to have a constant value that we apply. All right, and then you calculate your QZ from that above equation, plugging in all the other factors that we determined earlier. All right, so here is just an example of a worksheet that was used to go through this example. And all the stuff that we've just talked about is filled in red. And then this is that table for determining KZ. So as you can see, there are different columns for the different exposure categories. So that's one thing you want to make sure to keep in mind, right? Make sure you select the correct exposure category to determine these values. And as you can see, the best case scenario, the one that gives the lowest KZ values, is exposure B, like we talked about before. And exposure D is the worst. As I mentioned before, if you fall in between any values, so like at the mean roof height for this structure, 111, we fall in between the table values, so you would just apply linear interpolation to get the 1.02 exposure coefficient. So then this is just showing the calculation, right? And then you get your QZ and QH values. So QZ is everything, right, from 0 to 111. QH is just QZ evaluated at 111. So that is the value, that 32, that's the value that you would use with the with the leeward walls and with the side walls. The windward wall, you would use all of the values in that far right column. All right, so now we've gone through steps 1 through 10 in that list. The next step would be to determine the external pressure coefficient. So the reason we need that external pressure coefficient is in order to calculate the design net pressures, which subtract the internal pressure from the external pressure. So our external pressure coefficient for the walls, we go to this table right here, right? We're going to enter with L over B for the leeward wall. So depending on the wind direction, right, and these are plan views showing here. So if the wind is perpendicular to the 200-foot face, then our L over B is 1 over 2. If our wind is parallel, then our L over B is 2. So we would pull the appropriate values from that table. And so for the, let's see, I don't think I skipped. Yeah, so we would just pull those values for the leeward wall, right? So we would have a negative 0.5 for one wind direction and a negative 0.3 for the other wind direction. Regardless of wind direction, we would have 0.8 for the windward wall and negative 0.7 for the leeward wall. So looking at first the wind perpendicular to the 200-foot face, then we have our, for our roof pressures, right, we need to know this H over L factor. And again, H is that mean roof height, which is 111 in this case. For wind direction perpendicular to the 200-foot face, L is 100. So our H over L is 1.1. And then we would pull those CP values, right? So this is where we have our H over L greater than 1. And so we have two zones that apply to the roof pressures. The first zone is from 0 to H over 2, which would be 56-ish feet. All right, so from 0 to 56 feet along the length of the roof, we would have that negative 1.3 factor apply. But we can reduce that because our roof area is going to be 100 times 200, which is greater than 1,000 square feet. So we can reduce it. So we get negative 1.3 times 0.8 is negative 1.04 for our CP factor. The second zone will be from 56 feet to H, or I guess in this case it just says greater than H over 2. So beyond the 56-foot mark along the length of the roof, we would use a CP of negative 0.7. So that's where those values come from in this table. And then for the other wind direction, our H over L is 0.6. So that gives us our, in the first category here, the first list, right, we fall into here. So we have up to 4 zones to consider. In this case, we won't be using all 4 zones because our building is not longer than 2H. So we'll have our first zone where we have to interpolate, right? Oh yeah, so that's right. So we interpolate because our H over L is in between these two values, right? So it's not less than or equal to 0.5, it's in between. So we have to interpolate between negative 0.9 and negative 1.3, which can be reduced to 1.04, right? So we interpolate between those two, get negative 0.93. The second zone, interpolate between negative 0.9 and negative 0.7. So we get negative 0.86. And the third zone, we interpolate between negative 0.5 and negative 0.7. So we get negative 0.54. So there's not going to be any fourth zone because the building ends before 2H, right? So 2H is what, 222? And the building's only 200 feet long, right? All right, so that's how we get these values for our wind pressures on the roof for this direction. So we got that done. Now we just need the enclosure classification, right? So we already decided that it's an enclosed building. Our internal pressure coefficient will be plus or minus 0.18. So we figured that out. And then we're ready to calculate the design net pressures, right? So that's summarized in this table here. So for wind perpendicular to the 100-foot face, let's see. All right, just gonna skip ahead, make sure I know what's coming. All right, so we've got, so first we'll look at the wind perpendicular to the 200-foot face. All right, so the way this table is set up, we've got the Z coordinate, right, which is the variable distance along the height of the building. Your Q associated with that, that's your velocity pressure coefficient. That's the velocity pressure, not coefficient. And then CP is your external pressure coefficient, right? So for the windward walls, just 0.8, and then for the other walls, we've got what we just determined and talked about. G is your gust effect factor, right? The capital G. This is only used for calculating the external pressure, right? So the external pressure is G times CP times QZ, right, or QH for these guys. So that's how you calculate the external pressures. The internal pressure is GCPI times QH, right? So QH is 32. Let's see, GCPI, yep. Yeah, so this is a little bit confusing because this table has these listed as plus GCPI minus GCPI. What these values are really showing is the net pressure. So we're taking the external pressure and subtracting the case of positive internal pressure, right? So the positive internal pressure is the 0.18 times 32. So 12.2 minus that is 6.4. The case of negative internal pressure, 12.2 minus negative 0.18 times 32 gives you 18. So that's how those values are calculated. So for wind perpendicular to the 100-foot face, it's very similar. I'll show you, it's easier to show graphically what's the same and what's different. So sketching those pressures for the wind perpendicular to the long side, we have the external, or let's see, these are the net pressures, right? The net pressures shown on the outside of the surface of the building. So for this wind direction, right, you see your windward values, the roof with the 2 pressure zones on it, and then your constant leeward values, side pressures shown in a plan view. And then for the case of negative internal pressure, right, versus positive internal pressure, you can see how the external, or the windward pressures are greater for the case of negative internal pressure, right? And remember, we talked about that. That's because for the windward wall, you got positive pressure acting on the outside, and you have negative pressure acting on the inside, so they act in the same direction. For the internal case, positive internal pressure, we have windward pressure acting in one direction and internal pressure acting in the other direction, so they kind of balance each other out to an extent, right? You'll have a net pressure still in that direction. And then on the opposite side, right, you have the leeward pressures are greater for the case of positive internal pressure compared to negative internal pressure. Same with the roof and the sidewalls. All right, so, another important thing to note is that when drawing these net pressures, right, so in the tables, they have a plus or minus associated with them, right? So the plus refers to a net positive pressure. And so this is in the context of the external pressure, right? So consistent with the external application, because we take the external pressure and we subtract the internal pressure, the sign on this would be with respect to the external direction or the external reference point. So this would be positive on the external surface of the windward pressure, negative on the external surface of the leeward inside and roof walls, right? So the signs are important to include in the tables when you calculate those values, but once you interpret those to a sketch, just forget about, right, don't include the signs on your sketch, but show the pressures acting in the actual direction that they're acting, right? So interpret that sign, but don't include it on your magnitudes. Just show the direction. So for wind perpendicular to the short side, right, the other direction, the windward pressures don't change at all, right? Because remember that CP value for windward is always 0.7 or 0.8, positive 0.8. It doesn't depend on the ratio of L over B. Same with the sidewalls, right? It's always going to be negative 0.7. It doesn't matter what direction the wind is blowing. So the roof and the leeward walls are the only pressures that will change with wind direction. So those are shown a little bit differently here for that new direction. All right, any questions? Okay. So the good news is you won't have to actually go through the process of doing a problem like this and calculating all these pressures. So in your homework, let me see, I'm going to try and pull this up here. I'm going to show you some fun things in a moment too, but I want to get homework discussion in here. Let's see. So, Here we go. There. All right, so got homework should be showing up here. Okay. So in your homework, first of all, on the cover page, you are given these sketches to represent the building that you're going to consider for homework 7 and also homework 8, which hasn't been released yet, but will be focused on snow loads, rain loads, and load combinations. So first problem is focused on dead and live loads. And you're going to be referencing, actually, you're going to also be referencing homework 2. So the floor system that was provided in homework 2 problem 4 is going to apply to this assignment. And you're just asked to use those ASCE load tables to determine different things that are asked for in here. So let's see, do I have those dead and live load ones in here, or just the external? I do. All right, so one thing I wanted to point out in this, right at the bottom here, I give you, right, the tables that are relevant to the problem, as well as which lecture and text chapters are relevant to the problem. So use your references, and let's see, up here, right, when you're calculating the dead load for this portion, this contribution, right, the 3.5-inch reinforced stone concrete, I specifically say to refer to table C31-2, which is in your dead and live loads handout. It's this table that provides the densities, right? So for the other things, you'll be using the first table, which gives you the load in PSF for different types of coverings and finishes. But for that 3.5-inch stone concrete, I'm asking you to use this table, C3.1-2. All right, so you're basically going to be looking for concrete, and then what does it say? Stone reinforced? Yep, reinforced stone concrete. So going back to that, all right, so concrete, stone. All right, that gives you a density of 144 pounds per cubic foot. All right, so use that because there are some items in the other table that can be misleading. They don't apply. I think if you were to look, let's see, yeah, floor fill. So there's some concrete stuff that shows up under floor fill, and there's even one for stone concrete that's per inch. So that one actually would be okay to use as well, I think. Yeah, but I'm asking you specifically to use this table C3.1-2 for that. So keep that in mind when you get to that. And then your second problem will be on seismic loads. So for the seismic loads, you're going to be referencing this project building, right? So the story weights are provided, the story heights are provided. So that's the information you're going to need along with the other stuff that's included in the problem statement for seismic loads. And that's going to be pretty straightforward, just following that process for calculating seismic loads on that building, right? For the wind loads problem, all right, you don't have to calculate those net design pressures that we just talked about and went through that example on how to get them. You don't have to calculate those for this problem. They're already provided. So what you're going to be doing in this problem is taking those pressures and then distributing them through the lateral force resisting system. All right, so this problem will walk you through that concept, but it's also going to ask you to think back to those lectures that we did at the beginning of the semester, and we talked about load paths, and tributary areas, tributary widths, tributary heights would be applicable in this case, all right? So for a lateral force like wind pressure, it would be tributary height to each diaphragm that you would take and multiply that wind pressure by to get a line load that would act on the diaphragm. And then from there, you can calculate the total load that's acting at a given level of the building, and then this kind of talks you through that process of summing that up to get the wind-based shear. And it's actually going to have you check your results using a different calculation. So it's going to go through that process and walk you through it. And then for extra credit, right, you can use the information that's given and try to play detective and find some of these other pieces of information that would be used to calculate this, all right? So you can be creative, right? Think outside the box. You don't have to necessarily calculate everything the way that we did, all right? See if you can understand the differences between positive internal and negative internal cases, right? So these are net pressures, but for the case of positive internal pressure and for the case of negative internal pressure. So you can use that, if you understand what's going on there, to kind of use it as a shortcut to figuring out some of these things, right? And then other things you'll have to, pull from tables, or, there will be some calculations involved. But anyway, opportunity for extra credit in this assignment. And then the last page of the assignment is related to that wind loads problem. So it just shows you graphically, right, what you're doing. You're taking the pressures on the windward and leeward walls, calculating the line loads on the diaphragms, and then figuring out the total forces at each level. So any questions on the homework? Okay. All right, so I know there's 1 minute left, but I did want to show you, I had some pictures of wind tunnel studies, all right? So these are actual wind tunnel models that have been created for various structures. So you can see, some of them are very detailed, and others are a little bit less detailed. Here's one with several tall buildings in it, right? I'm trying to find one. So there's some that, so you can see how, right, this is modeling an entire urban center, and then to represent the surroundings, you've got just a bunch of smaller obstructions down there. And then, I was going to show you guys a video, but I don't think we have time for that. But here is, maybe I'll show it next time. Here's a video or a image. Oh, all right. What's that? Just a document? All right. Well, anyway, next time I'll show you a cool video of a wind tunnel test, and then some other wind-related things. And then we'll start talking about snow loads. So that'll be a fun topic. All right. See you Friday.